Okay, up next we have Professor Mark Modera.
Okay, so the bad news is I learned about this last night that I'm giving this talk. And my sort of activity within the project has been pretty close to zero up until last night. So that's the bad news. The good news is, because of that, there's not going to be much color or discussion, so I might catch us up on time. So let's see what we can do. So basically, my talk for today is about smart power for the smart home. It's a project that's mostly at UCI. And by the way, it was there was a family emergency thing. That's why the speaker's not here. And I live here, so it was easier for me to come give the talk. I'm the PI at UC Davis, but our part of the project hasn't even started yet. So what we have is the idea of the project, and why don't I just sort of jump into it. It's between UCI and UC Davis. I'm the director of the Western Cooling Efficiency Center, and GP Lee is the director of CalPlug, or the Plug Load Center. So let's see. So basically, this is sort of the problem statement. Capacitance and inductance create and consume reactive power. Reactive power is going to introduce problems with maintaining a robust grid. And at least up until now, the utilities have not figured out an acceptable way to charge customers for reactive power, despite the fact that they have to provide it. Because they can't charge them, the consumers are not exactly concerned about it. Almost as bad as me with my Tesla, right? Where I'm not concerned about the battery because there's a warranty, right? Which I'm not so sure if I'm going to go that route anymore. But the idea is it doesn't cost the consumer anything, and it's not their job to maintain the grid. And so the goal of this project is to enable smart management of the loads for zero net energy residences, and to be able to do that essentially as a way to make the grid work better and without having to charge the consumer a bunch of money to do it. Rough order of magnitude things, about 30% of natural electricity is for residences. This statistic, I didn't check it. I'm assuming they were right, that by the second quarter of 2014, which already happened, there should have been about 16 gigawatts of PV installed, which is enough to power about 3.2 million homes. So the challenge is that PV is an intermittent energy source, and various plug loads can cause the power factor to fluctuate. So you get sort of two separate problems. One is you get the PV coming on when it wants to, when the sun shines, and you've got plug loads that can cause poor power factors. The idea of the project is to do active power factor correction at the PV inverter, and also to do in-home ADR, or automated demand response. So basically, there are two things that are happening. One is you've got the active power factor correction, and the other is to do a load signature analysis for wireless load monitoring control. In other words, keep track of what your loads are doing. This is not necessarily all that new of an idea. I've been around long enough. There were people playing with this at MIT about 30 years ago. But nobody seems to have nailed it yet, as far as I know, anyway. The idea, and this is where my center comes in, is the nastiest load in this whole thing is the cooling system. And the cooling system is very large, right? And it comes on, and it's shifted by about 3 hours relative to the solar. So you get maximum solar production, and then you've got the problem that you don't need that much air conditioning right then, but in a few hours you will. And so in my research group, we've done things looking at different sides of thermal storage, right? And there's also people looking at battery storage, right, to basically use used car batteries inside houses as a way to deal with that problem. So, and this I'm assuming is correct. I didn't go check it in the last 12 hours. Typical PV inverter provides active power only. And the reactive power from any of the loads is passed to the grid. And so in a net zero energy situation, you're effectively giving mostly reactive power to utilities, and they cannot charge you for that. And the idea here is to put in an active power filter that can cancel that reactive power. The way I guess we analogous to noise canceling microphones, noise canceling headphones, excuse me. So, and like I said, there's not much color here. I mean, I understand what all those things are, but not much I can tell you about it. But the key I can tell you is what you want to do is you want to get rid of the reactive load as well as the harmonic components. You want to get a power factor close to 1 as far as the grid is concerned. And the end result is that everybody's happy. So this is the automated power factor objectives. To have something that can run at 1.5 kilowatts, and I don't know exactly where they are. The idea is to test this and fine-tune it in the lab, do a real circuit demonstration, and the idea is to make this be something that can be used for a retrofit. Once this is completed, we then go to an inverter with APF functions built in, and this is where we come in. We'll actually do the field monitoring to see what that does in a house. We have a house, actually a net zero energy house, probably 100 yards from my office. So it's very convenient for us to be able to do that. Now we've switched gears a little bit. We've switched from the power factor sort of correction to load signature. And you've heard a little bit about this already, about there being little to no incentive for end users to shift, mostly because there's not time-of-day pricing. And you've heard all that before. So now, in terms of what we would do, and this is the UCI part of it, provide the utility with end-use information for billing, efficiency program marketing, or demand response control, and provide consumption data back to the user. So this is all, the idea is to put both of these are sort of two separate objectives in the same house. The way that this is occurring is use energy metering integrated circuit to measure real and reactive power and to track and categorize appliances. So basically, you're tracking what your appliances look like, but not only in terms of time of day, but also in how they split between real and reactive power. And then the other thing they're doing is looking at the first 15-second waveform to be able to identify what it is that's turning on. Then finally, use fast Fourier transform to figure out the harmonics. That stuff I do know about. And essentially, it's try to do a smarter job than was being done 30 years ago of figuring out what's going on inside the house. Like I said, not a lot. This is just sort of a nice diagram of showing this. And there's probably not that much more to say other than what I've said. You'll build a library, basically by essentially figuring out the signature of the various devices. And then you'll have a mobile interface. And I do not know, unfortunately, exactly where they are on that. So in terms of our part of the project, UC Davis will do the field demonstration, as I said, at the Honda Smart House, which is, like I said, right across from our facility. And what we'll do is install the device. We will monitor the energy flows and the efficiencies, look at how good of a job it does on the power factor correction. And we already have data coming from that house. And the idea is that we'll look and see how much better we can make that with this new addition. And the home, people have moved into it, I think 2 months ago, something like that. So it actually it's a net zero home. It's on campus. It was basically just something to show people, but now there's a family living there. And so we'll also talk to the owners of the house and see what they think. And then finally, the other thing that we will do is we'll create an Energy Plus model. Well, we have an Energy Plus model for Z&E Home. But what we'll do is we'll look at all of the, if you like, the mechanical engineering side of this and figure out how well that can integrate with the electrical engineering side, which is what they're doing at UCI. And as I said, I would catch us up. So I think I did so. I'm sorry for not much content. I apologize. There were things I actually do know about, but this wasn't one of them. If there are any questions, I can deflect with the best of them.
Well, question mark, Chris Scruton. As equipment efficiency improves, there's a sort of been a transition from split phase induction motors towards permanent magnet motors, and I wondered if you knew what effect does that have on the power factor issue? Are permanent magnet motors better on reactive power than induction?
I have no idea, unfortunately. One thing I do know that's related to that is there are actually manufacturers like Daikin that make inverters and run DC compressors. So they take the AC, they invert it back to DC, and they use the DC to run variable speed on their compressors. So that, I think, is an interesting interaction. And it's not part of what we're talking about today, but the idea of actually having a DC house, right, rather than an AC house. Because then you've got to go through, you're basically, the solar comes in as DC, inverted to create AC, and then take that and go back down and create DC. And so that's something I think is worth looking at. And I believe we have Daikin equipment in that house. So I'm not sure how far we'll go with trying to play with that.
My name is Taufik from Kapolri San Luis Obispo. The APFC that you were talking about, does this device have the ability to change power factor instead of just one? Because having power factor just one doesn't always mean good for the grid, right? Because you want, for example, a smart inverter will be able to adjust reactive power based on the condition on the grid. So I'm just wondering if that would be the...
So let me try to restate your question. I think what you said is, did I promise to create a power factor of 1? And as I understood it, that was the goal. But then the other part of your question is, well, suppose you want the power factor to go the other way, right? Can you do that? And I don't know the answer to that. In other words, you can be more reactive or less reactive, and the grid could want more or less of the other. And I don't know the answer to that. What I think would be good would be to sort of transfer these questions over to the team at UCI. It was the UCI professor was supposed to give the talk today. Oh, that was a fellow there who had his hand up. Okay.
Yeah, I can just reply to that. I mean, most of the inverters today that will be sold in the market have all VAR compensation to help the grid to mitigate all kinds of changes in the current. So if you decide to go to closer to 1 power factor, that's you pay the price of not harvesting the watts versus the VARs. So you can go lower than that. It depends on what's at the end of the day, the standards going to dictate the maximum distortion in the line, because some of those loads are non-linear. Therefore, it's not only the shift that you can monitor and you can be flexible, it's the harmonics you push in. So if you are within the standards, you can be flexible, but you cannot, of course, avoid that range of allowed harmonics to be added.
Thank you. That fellow's raised his hand a bunch of times in the back.
Your load device analysis identification, is it based purely on having a library of other devices, or would you have a training session where the user would say, I'm going to turn on my washing machine now? Because it would seem that would be more effective than just assuming from an average what device you're identifying.
I don't know the answer to that. I can tell you with my grad student, we're doing things like, doing stuff like turning on the thermostat in the middle of the night and watching the response of the house so you can actively identify what's going on. It's a little easier to do system identification if you do perturbations of the system, which is basically what you're saying. And I don't know how far along they are to know if you can do a good enough job without the perturbations versus with the perturbations, the learning process.
Great, thank you, Mark.
Okay.